So Einstein had to do a little bit of work in order to derive our new expressions for energy that work properly under a Lorentz transformation. Just as a matter of review, just think back to what is kinetic energy, right? Kinetic energy is 1/2 mv squared. That's classical kinetic energy. Classic kinetic energy is 1/2 mv squared. That is no longer our form of kinetic energy. So where did that come from? Do you remember how we derived that? I'll give you a second or take a pause, but we derived it from the definition of work. I guess we could do this in 3 dimensions. We derived it from the definition of work, and we said the work energy theorem says that work equals change in kinetic energy. Work is defined as change in kinetic energy, and work is also defined as F dot dr, and we could put in ma for F, and that's where Ke equals 1/2 mv squared comes from. But no longer ma, F is now d dt of gamma m0u, and dot dot dot, we can do the math. It takes a little bit of effort, but you can absolutely do it. You could plug that in and figure it out. The dot 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 is a little long. It's a page for me, 1, 2, 3, 4, 5, 6, no, 7, 8, 9, maybe 9 lines of math, but it does require integration by parts. So it's not trivial, but in order to get it to the end, what we end up with is relativistic kinetic energy, dot dot dot, is, and again, I challenge you to calculate it on your own just using this stuff. But anyway, relativistic kinetic energy ends up being gamma mc squared minus mc squared, or gamma minus 1 times mc squared, where again, gamma is equal to 1 over the square root of 1 minus u squared over c squared, where u is the speed of the particle. So that is a bizarrely different function than the 1/2 mv squared we see at the top. Wow, that's different. But let's just say, oh wait. One of the things that must be true is at low speeds, all of the relativistic things must be equal to the the classical things. So let's see what this is at low speeds, right? K relativistic is equal to gamma minus 1 mc squared, which is 1 over the square root of 1 minus u squared over c squared, minus 1 times mc squared, which is 1 plus 1/2 u squared over c squared. So this is the approximation, right? That minus 1. Wait a second. Wait. Okay. mc squared. Okay, so all I did was I did the binomial approximation on this guy and made it into this guy, because u is much, much less than c. If we're not in the relativistic realm, u is much, much less than c. And so what are we left with? What we are left with is 1 minus 1, so 1/2 u squared over c squared mc squared. Okay, look at that. That's 1/2 m u squared. Check. So that is the classical form. So the relativistic form, which looks very different, turns into the classical form for speeds that are non-relativistic or low speeds. Okay, so let's see what this relativistic kinetic energy does for us. So what Einstein recognized is when you look at the relativistic kinetic energy, which just comes from the definition of work and the work energy theorem, it's got 2 terms now, right? Before it only had 1 term, but it has 2 terms now. This term, which is a gamma mc squared, and this term, which is an mc squared. And what Einstein recognized is that this can be taken out and is the total energy, whereas this is what he called the rest energy. In other words, what Einstein recognized is that the total energy is equal to gamma mc squared, which is K plus mc squared, which is the kinetic energy plus what's called the rest energy. I should say this is defined, right? So Einstein just defines the first term, gamma mc squared, as the total energy, and then shows that therefore, if gamma mc squared is the total energy, it must be the kinetic energy plus mc squared. So what is this total energy and this rest energy? All right. So you have heard the famous Einstein energy, E equals mc squared, right? Well, it's a little bit of a misnomer because look what E is. E, according to Einstein, is gamma mc squared, or it's K plus mc squared, or it's mc squared, depending on the situation. So we need to pick apart these things. What we have is that the E equals mc squared, that is actually the rest mass. And really this should be m0. I think that should be a given, but this m, whenever you see an m, that's the rest mass. That's the rest mass. I might have said rest mass earlier when I meant rest energy. Okay, so that's the rest mass. And the rest energy is mc squared. So E0 equals E0, the rest energy, equals m0, the rest mass, times c squared. That's what you always hear about Einstein's energy equation. And what that says, what that particular thing says, is that a body at rest has an energy associated with it. This body here is supposed to be a book. I don't think that's obvious, but it is a book. So I wanted to choose any body with mass, right? Mass, and let's just say it has got a mass, which when I put it on a scale, that must be its rest mass because that's rest relative to the scale, m0. So there's nothing special about rest mass, right? It's just when you put something on a scale, if it's not moving relative to the scale, that's the mass that is rest mass. Okay, it's got a rest energy. What is that rest energy? The rest energy is mc squared. What does that mean? It means it's got an energy associated with it that's equal to mc squared. What it means in practice, well, it means more than this. What it means in practice is that if we annihilated that book, if we turned that book into energy, not burn it in a fire, but if we were able to turn all the atoms and molecules, all the nuclei, all the electrons, protons, and neutrons into energy, that we would get out this much energy out of the book. That's what Einstein was able to show. And that if the book is going faster than zero speed, if it's not resting, then it has this much energy in it that can be used, that can be taken out. Now, when we say a massive body has rest energy that can be used, if we annihilate it, well, how do you actually turn a body into energy? That's not easy at all. That's really hard to do. Happens all the time naturally in atoms, in some kinds of atoms, but it's not easy to do. That's why I use the word annihilate. Annihilate is actually a physics term. I mean, it means other things in other parts of language, but it's a physics term. And what it means is when you annihilate a mass, you can take a particle and its antiparticle. If you put together, and this is true physics, they use it in the movies all the time. If you take a particle and its antiparticle and you put those two together, they will turn into photons. They will turn into energy. Photons are energy. Don't know if we've said that before. But photons are energy. Massless particles, right? The mass will go away and it'll turn into energy. What's the only massless particles that we currently really are aware of? You're aware that there are others, but photons. So you can annihilate. If you get an electron and an anti-electron, and you put those two together, you get energy out. You get photons out. You get massless particles out that therefore can only have kinetic energy. Or a kinetic energy, or they can only that has energy that you can then turn into work. And same thing with protons and neutrons. Each of the particles has an antiparticle. Now, why doesn't this happen all the time? Why doesn't Dagum find an anti-Dagum and the two of them gets together and he gets annihilated and turns into energy and just disappears? Well, that's because the antiparticles are actually hard to find. There's not a lot of antiparticles around. We can create them in the lab, but there's not a lot of antiparticles around. We don't have a lot of time to go into these details, but a place where mass is turned into energy all the time is in a nuclear reaction. That's the whole point of what Einstein had to do his work before we could create nuclear reactors and before we could create nuclear bombs, because the energy that comes out of the nuclear reactor or the nuclear bomb is the energy due to turning mass into energy. So just to get a sense of the size of the rest energy, Einstein's rest energy compared to the chemical energy you might get out of burning a piece of wood or something, or burning Nick. Let's not burn Nick, but how much rest energy is in Nick? Well, I don't know what Nick's mass is, but let's say that Nick's mass is about 70 kilograms. If Nick's mass is about 70 kilograms, what's that? 140? That's about 155 pounds. That's about 155 pounds. Okay. So Nick's mass is 70 kilograms. Therefore, it's easy, and that's his rest mass. You know, he's at rest relative to a scale. So we can figure out the rest energy is 70 kilograms mc squared times 3 times 10 to the 8th meters per second, quantity squared, and that number is, so that's 6.3 times 10 to the 18th joules. Is that a lot of energy? Is that a lot of energy? Well, let's think about it in terms of a scale that maybe we do know. Starting with, it takes, if you have a 1 kilogram mass, it takes 1 joule to lift a 1 kilogram, wait a second, is that right? No, sorry, it takes 10 joules to lift a 1 kilogram mass 1 meter, because energy is equal to mgh in that case, and that is 1 kilogram times 10 meters per second squared times 1 meter, which is 10 joules, or 9.8 joules because I rounded. But anyway, 10 joules. And this is 6.3 times 10 to the 18th joules. Sounds like it might be a lot. Let's think about a power plant. Let's take a typical power plant. Let's say you have a 500 megawatt power plant. I can't really remember if that's big or small, but it is a reasonable size for a power plant, nuclear power plant, hydroelectric power plant, whatever, 500 megawatt power plant. Well, that's power, right? That's the amount of energy per unit time. Mega, 10 to the 6th, watts, joules per second. So that is 5 times 10 to the 8th joules per second. So in that power plant, we're creating 5 times 10 to the 8th joules per second. So therefore, how long does it take for it to generate 6.3 times 10 to the 18th joules? Therefore, the time that it takes to generate 6.3 times 10 to the 18th joules is 6.3 times 10 to the 18th joules divided by 5 times 10 to the 8th joules per second. And that's going to give us the amount of time. Okay, so it would take a 500 megawatt power plant, which may be a smallish plant, or 1.26 times 10 to the 10th seconds to generate the amount of energy that we would get from annihilating Nick, whoever, anybody who's 70 kilograms. So is that a long time? Well, just as a matter of scale, 1 year, this is a good number to remember, is approximately equal to pi times 10 to the 7th seconds. You can always figure that out, 365 times 74 times 3600, but it's about pi times 10 to the 7th. So this is about 400 years. I think that means that's about 400 years. So a 500 megawatt power plant would have to run for 400 years to generate the amount of energy that we would get from annihilating a 70 kilogram mass. Whoo-wee. So that rest energy, it's a very different thing than chemical energy, right? You're not going to get out very much energy if we burn a 70 kilogram mass. But that rest energy, the total energy that's inherent in the body due to the fact that it has mass, is humongous. And it is correct. Don't get me wrong here. Einstein showed that this was true, and that you could account for missing mass in nuclear reactions that turns into energy, and hence that's why nuclear power and nuclear bombs are so strong, because those are reactions where we're actually turning mass into energy.